안녕하십니까, 어느 아마추어입니다. 예, 이 밤늦은 시간에 제가 앞에 시작과 끝을 일직선상으로 이제 설명을 하다 보니까 약간 설명이 부족한 것 같아서 여기 설명이 될 만한 좋은 영상이 하나 있어서 한번 들고 와 봤어요. 여기 보시면 뭐 파이가 왜 여기 있지, 뭐 왜 그리고 왜 사각형이지, 여기 지오메트리 나오죠. 그 바젤 문제에 대한 그 지오메트리 기하학적 답변인데, 이게 무한급수에 대한 그 무한급수의 합에 대한 설명이 나와 있어요. 그러니까 직선적으로 봤을 때 직선이 이게 우리가 시작과 끝을 했을 때 시작에 처음 선과 끝선이 있지 않습니까? 그게 왜 원으로 해석이 될 수 있는지 앞에 또 우로보로스를 제가 얘기 드렸죠. 그러니까 왜 직선과 수직선과 원의 관계에 대해서 자세하게 설명이 되어 있어요. 제가 수학적으로 이제 전문가가 아니기 때문에 영상으로 한번 보시고, 약간 이게 지루할 수도 있습니다. 예, 일단 같이 한번 보실까요?
I'm gonna guess that you have never had the experience of your heart rate increasing in excitement while you are imagining an infinitely large lake with lighthouses around it. Well, if you feel anything like I do about math, that is gonna change by the end of this video. Take 1 plus a fourth plus 1/9 plus 1/16, and so on, where you're adding the inverses of the next square number. What does this sum approach as you keep adding on more and more terms? Now, this is a challenge that remained unsolved for 90 years after it was initially posed, until finally it was Euler who found the answer, super surprisingly, to be pi squared divided by 6. I mean, isn't that crazy? What is pi doing here? And why is it squared? We don't usually see it squared. In honor of Euler, whose hometown was Basel, this infinite sum is often referred to as the Basel problem. But the proof that I'd like to show you is very different from the one that Euler had. I've said in a previous video that whenever you see pi show up, there will be some connection to circles. And there are those who like to say that pi is not fundamentally about circles, and insisting on connecting equations like these ones with a geometric intuition stems from a stubborn insistence on only understanding pi in the context where we first discovered it. And that's all well and good, but whatever your own perspective holds as fundamental, the fact is, pi is very much tied to circles. So if you see it show up, there will be a path somewhere in the massive interconnected web of mathematics leading you back to circles and geometry. The question is just how long and convoluted that path might be. And in the case of the Basel problem, it's a lot shorter than you might first think. And it all starts with light. Here's the basic idea. Imagine standing at the origin of a positive number line and putting a little lighthouse on all of the positive integers, 1, 2, 3, 4, and so on. That first lighthouse has some apparent brightness from your point of view, some amount of energy that your eye is receiving from the light per unit time. And let's just call that a brightness of 1. For reasons I'll explain shortly, the apparent brightness of the second lighthouse is 1/4 as much as the first, and the apparent brightness of the third is 1/9 as much as the first, and then 1/16, and so on. And you can probably see why this is useful for the Basel problem. It gives us a physical representation of what's being asked. Since the brightness received from the whole infinite line of lighthouses is going to be 1 plus a fourth plus a 9th plus a 16th, and so on. So the result that we are aiming to show is that this total brightness is equal to pi squared divided by 6 times the brightness of that first lighthouse. And at first that might seem useless. I mean, we're just re-asking the same original question. But the progress comes from a new question that this framing raises. Are there ways that we can rearrange these lighthouses that don't change the total brightness for the observer? And if so, can you show this to be equivalent to a setup that's somehow easier to compute? To start, let's be clear about what we mean when we reference apparent brightness to an observer. Imagine a little screen, which maybe represents the retina of your eye or a digital camera sensor, something like that. You could ask, what proportion of the rays coming out of the source hit that screen? Or phrased differently, what is the angle between the ray hitting the bottom of that screen and the ray hitting the top? Or rather, since we should be thinking of these lights as being in 3 dimensions, it might be more accurate to ask, what is the angle the light covers in both directions perpendicular to the source? In spherical geometry, you sometimes talk about the solid angle of a shape, which is the proportion of a sphere it covers as viewed from a given point. You see, the first of 2 places this story where thinking of screens is going to be useful is in understanding the inverse square law, which is a distinctly 3-dimensional phenomenon. Think of all of the rays of light hitting a screen 1 unit away from the source. As you double the distance, those rays will now cover an area with twice the width and twice the height. So it would take 4 copies of that original screen to receive the same rays at that distance. And so each individual one receives 1/4 as much light. This is the sense in which I mean a light would appear 1/4 as bright 2 times the distance away. Likewise, when you're 3 times farther away, you would need 9 copies of that original screen to receive the same rays, so each individual screen only receives 1/9 as much light. And this pattern continues. Because the area hit by a light increases by the square of the distance, the brightness of that light decreases by the inverse square of that distance. And as I'm sure many of you know, this inverse square law is not at all special to light. It pops up whenever you have some kind of quantity that spreads out evenly from a point source, whether that's sound or heat or a radio signal, things like that. And remember, it's because of this inverse square law that an infinite array of evenly spaced lighthouses physically implements the Basel problem. But again, what we need if we're going to make any progress here is to understand how we can manipulate setups with light sources like this without changing the total brightness for the observer. And the key building block is an especially nice way to transform a single lighthouse into 2. Think of an observer at the origin of the XY plane and a single lighthouse sitting out somewhere on that plane. Now draw a line from that lighthouse to the observer, and then another line perpendicular to that one at the lighthouse. Now place 2 lighthouses where this new line intersects the coordinate axes, which I'll go ahead and call Lighthouse A over here on the left, and Lighthouse B on the upper side. It turns out, and you'll see why this is true in just a minute, the brightness that the observer experiences from that first lighthouse is equal to the combined brightness experienced from lighthouses A and B together. And I should say, by the way, that the standing assumption throughout this video is that all lighthouses are equivalent. They're using the same light bulb, emanating the same power, all of that. So, in other words, assigning variables to things here, if we call the distance from the observer to lighthouse A, little a, and the distance from the observer to lighthouse B, little b, and the distance to the first lighthouse, h, we have the relation 1 over a squared plus 1 over b squared equals 1 over h squared. This is the much less well-known inverse Pythagorean theorem, which some of you may recognize from Mathologer's most recent, and I'll say most excellent, video on the many cousins of the Pythagorean theorem. Pretty cool relation, don't you think? And if you're a mathematician at heart, you might be asking right now how you prove it. And there are some straightforward ways where you express the triangle's area in 2 separate ways and apply the usual Pythagorean theorem. But there is another quite pretty method that I'd like to briefly outline here that falls much more nicely into our storyline, because again, it uses intuitions of light and screens. Imagine scaling down the whole right triangle into a tinier version, and think of this miniature hypotenuse as a screen receiving light from the first lighthouse. If you reshape that screen to be the combination of the 2 legs of the miniature triangle, like this, well, it still receives the same amount of light, right? I mean, the rays of light hitting one of those 2 legs are precisely the same as the rays that hit the hypotenuse. Then the key is that the amount of light from the first lighthouse that hits this left side, the limited angle of rays that end up hitting that screen, is exactly the same as the amount of light over here coming from lighthouse A, which hits that side. It'll be the same angle of rays. And symmetrically, the amount of light from the first house hitting the bottom portion of our screen is the same as the amount of light hitting that portion from lighthouse B. Why, you might ask? Well, it's a matter of similar triangles. This animation already gives you a strong hint for how it works, And we've also left a link in the description to a simple GeoGebra applet for those of you who want to think this through in a slightly more interactive environment. And in playing with that, one important fact here that you'll be able to see is that the similar triangles only apply in the limiting case for a very tiny screen. All right, buckle up now, because here's where things get good. We've got this inverse Pythagorean theorem, right? And that's going to let us transform a single lighthouse into two others without changing the brightness experienced by the observer. With that in hand, and no small amount of cleverness, we can use this to build up the infinite array that we need. Picture yourself at the edge of a circular lake directly opposite a lighthouse. We're going to want it to be the case that the distance between you and the lighthouse along the border of the lake is 1. So we'll say the lake has a circumference of 2. Now the apparent brightness is 1 divided by the diameter squared. And in this case, the diameter is that circumference, 2, divided by pi. So the apparent brightness works out to be pi squared divided by 4. Now for our first transformation, draw a new circle twice as big, so circumference 4, and draw a tangent line to the top of the small circle. Then replace the original lighthouse with 2 new ones where this tangent line intersects the larger circle. An important fact from geometry that we'll be using over and over here is that if you take the diameter of a circle and form a triangle with any point on the circle, the angle at that new point will always be 90 degrees. The significance of that in our diagram here is that it means the inverse Pythagorean theorem applies, and the brightness from those 2 new lighthouses equals the brightness from the first one, namely pi squared divided by 4. As the next step, draw a new circle twice as big as the last, with a circumference 8. Now for each lighthouse, take a line from that lighthouse through the top of the smaller circle, which is the center of the larger circle, and consider the 2 points where that intersects with the larger circle. Again, since this line is a diameter of that large circle, then the lines from those 2 new points to the observer are going to form a right angle. Likewise, by looking at this right triangle here, whose hypotenuse is the diameter of the smaller circle, you can see that the line from the observer to that original lighthouse is at a right angle with a new long line that we drew. Good news, right? Because that means we can apply the inverse Pythagorean theorem, and that means that the apparent brightness from the original lighthouse is the same as the combined brightness from the 2 newer ones. And of course, you can do that same thing over on the other side, drawing a line through the top of the smaller circle and getting 2 new lighthouses on the larger circle. And even nicer, these 4 lighthouses are all going to be evenly spaced around the lake. Why? Well, the lines from those lighthouses to the center are at 90-degree angles with each other. So, since things are symmetric left to right, that means that the distances along the circumference are 1, 2, 2, 2, and 1. All right, you might see where this is going, but I want to walk through this for just one more step. You draw a circle twice as big, so circumference of 16 now, and for each lighthouse, you draw a line from that lighthouse through the top of the smaller circle, which is the center of the bigger circle, and then create 2 new lighthouses where that line intersects with the larger circle. Just as before, because the long line is a diameter of the big circle, those 2 new lighthouses make a right angle with the observer, right? And just as before, the line from the observer to the original lighthouse is perpendicular to the long line. And those are the 2 facts that justify us in using the inverse Pythagorean theorem. But what might not be as clear is that when you do this for all of the lighthouses to get 8 new ones on the big lake, those 8 new lighthouses are going to be evenly spaced. This is the final bit of geometry proofiness before the final thrust. To see this, remember that if you draw lines from 2 adjacent lighthouses on the small lake to the center, they make a 90-degree angle. If instead, you draw lines to a point anywhere on the circumference of the circle that's not between them, the very useful inscribed angle theorem from geometry tells us that this will be exactly half of the angle that they make with the center, in this case 45 degrees. But when we position that new point at the top of the lake, these are the 2 lines which define the position of the new lighthouses on the larger lake. What that means then is that when you draw lines from those 8 new lighthouses into the center, they divide the circle evenly into 45-degree angle pieces. And that means the 8 lighthouses are evenly spaced around the circumference, with a distance of 2 between each one of them. And now, just imagine this thing playing on. At every step, doubling the size of each circle, and transforming each lighthouse into 2 new ones along a line drawn through the center of the larger circle. At every step, the apparent brightness to the observer remains the same, pi squared over 4, and at every step, the lighthouses remain evenly spaced with a distance 2 between each one of them on the circumference. And in the limit, what we're getting here is a flat horizontal line with an infinite number of lighthouses evenly spaced in both directions. And because the apparent brightness was pi squared over 4 the entire way, that will also be true in this limiting case. And this gives us a pretty awesome infinite series, the sum of the inverse squares 1 over n squared, where n covers all of the odd integers, 1, 3, 5, and so on, but also -1, -3, -5, off in the leftward direction. Adding all of those up is going to give us pi squared over 4. That's amazing, and it's the core of what I want to show you. And just take a step back and think about how unreal this seems. The sum of simple fractions that at first sight have nothing to do with geometry, nothing to do with circles at all, apparently, gives us this result that's related to pi. Except now you can actually see what it has to do with geometry. The number line is kind of like a limit of ever-growing circles. And as you sum across that number line, making sure to sum all the way to infinity on either side, it's sort of like you're adding up along the boundary of an infinitely large circle, in a very loose but very fun way of speaking. But wait, you might say, this is not the sum that you promised us at the start of the video. And, well, you're right, we do have a little bit of thinking left. First things first, let's just restrict the sum to only being the positive odd numbers, which gets us pi squared divided by 8. Now the only difference between this and the sum that we're looking for, that goes over all the positive integers, odd and even, is that it's missing the sum of the reciprocals of even numbers, what I'm coloring in red up here. Now, you can think of that missing series as a scaled copy of the total series that we want, where each lighthouse moves to being twice as far away from the origin. 1 gets shifted to 2, 2 gets shifted to 4, 3 gets shifted to 6, and so on. And because that involves doubling the distance for every lighthouse, it means that the apparent brightness would be decreased by a factor of 4. And that's also relatively straightforward algebra. Going from the sum over all the integers to the sum over the even integers involves multiplying by 1/4. And what that means is that going from all the integers to the odd ones would be multiplying by 3/4, since the evens plus the odds have to give us the whole thing. So, if we just flip that around, that means going from the sum over the odd numbers to the sum over all positive integers requires multiplying by 4/3. So, taking that pi squared over 8, multiplying by 4/3, bada boom bada bing, we've got ourselves a solution to the Basel problem. Stick around, I've got a little preview animation for the next project at the end here. Now, this video that you just watched was primarily written and animated by one of the new 3 Blue 1 Brown team members, Ben Hambrecht, an addition made possible thanks to you guys through Patreon. You'll meet him along with the other new addition when the